Okay, so for your test 2, your test 2 will be covering CL3, CL4, which is we'll look at rigid body, and then we look at Newton law, work energy equation, and principle of impulse momentum. So 2 questions for your test 2. Question 1 will be CL3, question 4 will be your question 2 will be CL4. Today we're going into chapter 8. Where we start to look at rigid body already. Okay. So now, previously, before this chapter, we are considering everything is in particles. But start from this chapter, we'll look at our object as rigid body. Okay. Now, when we look at rigid body means it's a body like your human body. You have head, you have your body, you have your leg, you have your hand. So we look into as a combination of all the components. So when we look at a previous chapter like particles, we sum up everything in one point. But when we come to chapter 5, when we look at rigid body, we have a few focus points. For example, the one that you see on the screen here, we have 2 points of interest for the bodies. Okay, so when we look at rigid body, we will see a few motion. The first motion is called translation. Translation. So translation means if you focus on these 2 points, the 2 points move in the straight line. Okay, this is called rectilinear translation. So means the motion move in the linear form, where the body remain parallel to its original orientation throughout the motion. Okay, so translation means the body remain parallel to its original orientation throughout the motion. Okay, means the body doesn't change orientation. Means if it's straight, then it's straight all the way. This is called translation. Okay, all right. Okay, so if it's moved in a curve, but orientation still the same, but in the curve, so we call curvilinear translation. So there are 2 types. One is linear translation, the orientation still same, but in the straight line. Another one is orientation still same, but in the curvilinear motion. Okay. Right. Again, we are now entering into rigid body and no longer particles. We are now in chapter 5, a new chapter where we look at rigid body. Okay. Another one, rigid body, it can rotate. Okay. Rotation, there must be an axis for it to rotate. Okay. So translation, rotation, and another one is called general plane motion. General plane is a combination of translation and rotation combined together. You get a general plane motion, where you can see on the diagram here. So the orientation of the object rotate and change plane. Rotate and change plane. It can be linear, it can be curvilinear, but the whole object change orientation when in the motion. Okay, so 3 motion: translation, rotation, and general plane motion. Okay, right. Okay. So we start to look at component, where no longer you cannot solve this question by rigid particles. You see it as a body. Body have a lot of component. So the first one, as you can see here, you're having a machine, a piston head, like in your lab, you do the piston, the experiment, right? The piston, you have a hole for it to move. So this one move, it already constrain the direction. So this piston move only in the straight line, this piston head. move in a straight line. So this is a rectilinear translation. The orientation is still the same, but in a linear motion. Okay. Then this one, the disc here, this disc rotate in a rotational manner at a fixed axis. So this body rotate. Okay. This arm also rotate. It was fixed to a point and it rotate. Okay. So this is a rotation. Okay. Then this is curvilinear translation. How we know this is curvilinear translation? Again, translation, it do not change orientation, right? So when this one move, right, it will still change. So this is curvilinear translation. Curvilinear translation. This is general plane. This one change rotation into linear. So this arm become combination of linear plane and motion. Okay, so there are three types of motion for rigid body: translation, rotation, and mix or general plane motion. So for rigid body, it is good that you're able to identify the motion before you solve the question, because each motion have its own set of equation. So if you are unable or you confused with the motion, then your solution you're not able to get the correct answer. Okay. When we look at body or rigid body, means that the body move from a reference plane, for example, a fixed location with its X and L with the O, and this object move from this point to a point. Okay, so means this object translate to this point, and the distance traveled from origin to the new location is RA for point A. So meaning on the body itself, you are focusing on 2 points. Again, we are now in the rigid body. So rigid body, you have a different interest point, no longer have 1 point, right? So it can be more than 2 points. In this case, on the screen here, you are seeing 2 points. So A translate from O to A. B, it can translate from A. It can translate somewhere from here to here or from O to B. In this case, we are referring to O. So we have RA and RB. And previously, in previous chapter, we introduced you the relative distance, which is RB stroke A. So our cheat code for R stroke A, we change the stroke become negative, right? So if you see RB stroke A equal RB minus RA, or you can build a vector triangular, you still get the same equation, right? So first position, in this case, our base point A. So vector, position vector RA, RB, and position of B respect to A, position of B respect to A, we write as R sub B stroke A. So it's a different answer if you write R A stroke B, not same as RB stroke A. So don't confuse with this one. And in your task, don't ask me to guess for you. Okay? Don't ask me to guess for you. So it's important you know which one is which one. Okay. Okay. So RB stroke A means you are from where? You are referring to B from A. For example, this one. RB stroke A, you are from A. You are referring to B, but from A. B is your arrowhead, A is your starting point. So it's important. So don't confuse with A stroke B or B stroke A. It will give you different answer. Okay. So in this case on the slide here is A and B. In a question that you see in your test, it will be an object or it will be a certain point. It will be a piston point. It will be a certain point. Okay. So in this case, we label as A and B. Okay. Sometimes in the question for your convenience, we will label as something else. Like for example, point. Sometimes we give you A and B also, right? Or sometimes we change it to P and Q, y and z, and so on. Okay. All right. So if you do the triangular or vector triangular, you'll get RB, which is the resultant vector equal to RA plus RB stroke A. This is a resultant equal to this vector plus this vector. Okay, starting to N is your resultant. How to reach from O to B? You need two vector. Addition of these two vector, RA plus this R. Okay, so that's why you get this one. Or you can straight away use the cheat code. Translate RB stroke A equal RB minus RA. Change the stroke become negative. If you lazy lah, okay, but it's still the same, reach the same vector equation. Okay, so for rigid body, first you need to establish where is your reference point, where is the body moving. Then the next step is to write the vector addition. Means where is the position from the reference point, and then establish the vector, reference vector, relative vector. Okay. Once we have the position, we can find velocity, like what we covered in chapter 1, 2, 3, or especially chapter 1. We derive position into velocity. How we get velocity? When we have position, how we get velocity? Integrate or differentiate? Differentiate, differentiate with time. Okay, this is S in chapter 1, your position. How you get V? V equal to ds dt. Same. Take this position, differentiate with time. So you have dot here, dot here, dot here. So you get velocity. So when you have dr dt, you get velocity. Dr dt, you get velocity. Dr dt, you get velocity. Okay, but this one is because it's a reference or relative. B from A, you write in this form rather than you can still write V B stroke A, but you still need to do the differentiation. Okay. But you know, when you do time differential, this reference A to B, dr dB in rigid body doesn't change. In rigid body, T equal 1, T equal 2, or T1, T2. If you label the same 2 point, like your eyes to your neck, your eyes or between the two eyes, the distance always same. No matter where you walk, the distance between your two eyes or two eyeball still the same. Okay. Let's say this is A, this is B, so this is R, B from A. R, B from A. So it will always same. The distance between your two eyeballs is always same. So when you differentiate with time, you will get 0. Okay, you'll get 0. Okay, so you can cancel the velocity, the relative velocity between the 2 points on the body. So you get VA and VB. VA will equal to VB on the body. Okay. So this is the second equation on the rigid body. Okay. This is translation. We have 3 motion: translation, rotation, and general plane. Now we are looking at translation. What is the definition of translation? Orientation remains same. When it moves, orientation remains same. That's why position, we get this one, and velocity between 2 points on the body remains same because orientation same. Okay, orientation same. Acceleration still same. We apply chapter 1 definition. How to get acceleration? A equal to dv dt. We take velocity time differential. All right. We differentiate this one. you will get acceleration B equal to acceleration A. This is in translation mode. Translation means orientation same. Okay, orientation same. Translation have two. One is linear, rectilinear motion or linear motion or curvilinear motion. But still same. The 2 point on the body still same. Okay. Only the position is a bit different because the position is from a reference point. So you have the R, B, stroke A for the position when you translate. Okay. Now we have clear translation. Yeah. So translation have three equation, which is this one, position from a reference point. So for translation, you start with, I will always start with RB stroke A equal RB minus A. I'll start with this equation or this equation, same. Then I will derive the equation into velocity. I will take this position, time differential, ds dt or the r dt. I will get this equation. And for translation, this one cancelled, becomes 0 because the distance between 2 points on the bodies remains same all the time. So we cancel the velocity of the reference. Then we further derive the acceleration by a equal to dv dt. Okay, so this is translation. Next, we look at rotation. Okay, rotation, we use right-hand rules again. We use right-hand rules again. So let's say we had a body and we have a point that rotate clockwise. Okay, we follow your thumb, your finger is a rotation head or direction. So for rotation, we know that P, when rotation, it rotate in a circular form. Okay, so when circular form, we will use angular motion. Okay. Okay. So this one, since the point is without dimension, a point, it cannot have an angular motion. Only lines and body undergo angular motion. So angular motion of a radius within the shaded plane. This is R. So when you can define a point, then there's a rotation or there's an angular motion on the body. Outside here don't have. Only you touch the body, then you have the angular motion. Okay. Okay. First equation. How we define rotation position? By using angle. By using angle. Right? Angle with a fixed reference. For example, this line. This is your starting point. So you measure your position, angular or rotation position by angle. So it switch from this point to this point. So you have an angle, right? So then you have a displacement. Displacement is like your S in chapter 1, your displacement. So the displacement is a change of angle. In this case, d theta. So we call it d theta as a change of angular displacement. Right. Okay. So again, this is a vector form. Vector have magnitude and direction. So for chapter 5, your rotation you can measure in degree, you can measure in radian, you can measure in revolution. Okay. So revolution, one revolution means one round, one circle, equal 360, equal to 2 pi radian. So this is a very basic you transform from one unit to another unit. Okay. Most of the time, your question you will see how many revolution or how many RPM, revolution per minute. Right. Okay. And direction is determined by right-hand rules. So you see your hand. So if your object moving in the anti-clockwise direction, if the point move following your fingers, your thumb is a direction or axis of rotation. Okay. Okay. So we have, when you have displacement, we have velocity, we have acceleration. Okay. So again, they are anti-clockwise. Then from displacement, we convert to velocity. So how we get velocity? With ds dt. In this case, what is your s? Your s is theta. So when you take the change of angle, differentiate with time, you get velocity. In this case, because it's a rotation, it's an angular change, so we name as angular velocity, or in short, we name as omega. This one. Okay, so you change from theta into omega, then it changes to alpha. Alpha is acceleration. Right? So you have angular displacement, angular velocity. In this case, angular velocity omega. Okay. Now omega, usually you will see in daily life where omega of angular velocity is RPM, revolution per minute. You will see this one on all the machine, RPM. This is omega. Okay. So you know how to convert back, right? Velocity back to displacement. It's the same. You do the integration, right? So same like chapter 1. You reverse here and there. Okay. So omega is a change of angle. So you time differentiate it. And positive is always following your right-hand rules, which is anti-clockwise positive. Okay. So this is a rigid body, a little bit different compared to the previous chapter. All right. Okay. So here I make a note there. The magnitude is in radian per second, or it can be, radian per second means how many, you change it to pi lah. Change it to pi. Okay. So when you have angular velocity, you can find acceleration where you time differentiate this one. You time differentiate or w dot, you get acceleration. Or you double differentiate the angle, then you get angular acceleration. In this case, we use alpha. Okay. Alpha equal to d omega dt. It's the same concept like chapter 1. A equal to dv dt. In this case, your velocity is omega. So you just d omega dt. It's the same. Okay, it's only introduce you the new parameter in rigid body. For rotation, we are using omega alpha to represent the motion and angle and angle. Okay, so it's the same. In chapter 1, your A equal to ds dt. Dv dt. Your A also equal to d square s over dt square. Same. Yeah. All right. So again, it's the same. Here, if your velocity decrease, you have a deceleration. In this case, if your omega or your velocity decrease, your alpha will be decreased. In this case, if your acceleration decrease, we call it deceleration. Okay, deceleration. Okay, so for this, again, we combine chapter 1 concept. But in this case, when we freeze the time, we can write a new equation. We pull the t to left-hand side, pull omega down, pull the t to left-hand side, pull the alpha down, equal the two equations, rearrange, you get alpha dt equal to d omega. It's the same. D, right? It's the same like what you see over there. Right. Okay. So at the end, you see alpha d theta equal to omega d omega. So it's the same like the equation that you see in chapter 1, A ds equal to v dv. When our shortcut from chapter 1 to chapter 5, from particles to rigid body, what do? You change s into r or theta. You change v equal to omega or R dot, or V something, also same, right? A in chapter 1, you will change to alpha, R double dot, or A. It's the same concept, huh? It's the same concept, only change the parameter. Same with here, you see, alpha is A, D theta is ds, omega is velocity, so V d omega, omega is V, so V dV. It's still the same concept, but this one is in rigid body. And this equation is for rotation. Okay, it's for rotation. Okay, the next one is constant angular acceleration. When you have a constant angular acceleration with this alpha, because in chapter 1, there is one case where your acceleration is constant, you derive a 3 Newton equation. Same with here. If you have constant angular acceleration, you still can derive. So you have these 3 equations, omega or your velocity, alpha is the acceleration, and this is when you freeze the time, you get alpha d theta equal to omega d omega. So still the same, you have these 3 equations. So when you do the same, you do integration and so on, you arrive at 3 Newton equation. I'm not going to go through the derivation steps, but if you view back the chapter 1 derivation for 3 Newton equation, you change the A, you change the S equal to theta, V equal to omega, A equal to alpha, you arrive the same format. First one, omega equal to omega O plus ACT. What you see in chapter 1? Chapter 1, first Newton equation, V equal to VO plus AT. This is from chapter 1. You change the V into omega. Okay? Second one, delta S or S2 minus S1 equal, or S0, S1 equal to VT, VOT plus half ACT squared. Okay? So you change theta, replace change the S become theta, change the omega become V, V become omega, acceleration become alpha. Same with the other one. Okay. The third one is V square equal to VO square plus 2A delta S, or change of S. Same, you change V to omega, A to alpha, S to theta, Okay, it will be the same. Huh? So as long as you see there's a constant angular velocity, then you can use these 3 to solve any unknown. Okay. Now you should be able to identify whether the question is constant acceleration or not. If your velocity change with the equation and your acceleration, these 3 cannot use because your acceleration changing. Okay. All right. Now the right? Theta motion